So far, we have discussed dynamic compressor operation in the uncontrolled state, that is, without any automatic process control or protection in the system. Having discussed those factors involved in compressor performance, design, and operation, we will now overview both compressor control and protection. As previously discussed, the objectives of any compressor end user, or in other words, your objectives, are to purchase and operate compressor with maximum reliability, maximum product throughput, maximum efficiency, at a minimum operating cost. To achieve these objectives, it becomes necessary to adjust the compressor throughput to certain values, since we have seen that the throughput will vary as a function of process system requirements. Now, there are essentially two options available to you to achieve this objective. You can adjust the process system energy requirement or adjust your compressor energy output. Process energy requirement can be changed by either adjusting the suction system resistance or the discharge system resistance. The most common type of resistance adjustment is known as discharge throttling. This process results from adjusting the pressure drop of a control valve in the discharge to change the compression ratio of the compressor. Observing any compressor curve, we can see that for a specified gas composition and inlet temperature, there exists one and only one throughput, as depicted in this example. This assumes the compressor speed and the inlet guide vane position, if applicable, are held constant. If we position a throttling valve on the discharge of the compressor system, we will see that the desired flow throughput can be obtained by throttling the valve. Obviously, energy is lost during this exercise via the throttled pressure drop across the valve. Another alternative would be to position the throttling valve in the compressor suction process system. We will demonstrate that this method of increasing system resistance is less energy exhaustive and will result in lower operating costs than in the case of the discharge throttling. An important fact to remember here is that both cases increase the system resistance. In the case of suction throttling, the suction system resistance is increased, but this results in a lower suction pressure at the compressor flanges. One fact that is often misunderstood is that the compressor curve describes the energy increase from the compressor inlet to discharge flange, and pressure must therefore be measured at the inlet and outlet of the compressor to directly assess its operation. Frequently, suction pressure is measured upstream of the suction throttle valve, and the operators are not aware of the actual pressure ratio that the compressor experiences. In summary, suction throttling will control the operating point of the compressor, but will expend less energy and reduce operating costs. The second control alternative available is that of varying the produced energy of the compressor. It is much more effective to change the compressor produced head than to throttle to accommodate any operation changes. Available methods of adjusting the compressor curve are curve change and adjustable guide vane changes. Changing the speed of the compressor allows to adjust the compressor head and throughput by following the fan laws as previously discussed, and which are shown here for a reminder. We'll get back to them in a later video. The speed change of the compressor can be accomplished with variable speed turbines, variable speed drives, and variable speed motors. Variable speed motors are becoming more popular as capital investment costs for variable frequency motors is reducing. Now, in the case of a constant speed motor driver, adjustable guide vanes can be employed, and they result in the same compressor operational flexibility. It is important to note here that inlet guide vanes are not throttle devices, but change the inlet angle of the gas to the impeller. This results in different produced energy values for a given compressor inlet flow. It should be noted that inlet guide vanes in series configuration multi-stage compressors can be employed only in the first stage. This is due to the fact of the limited accessibility for the necessary guide vane linkages. Integral gear compressors, however, can be designed with inlet as well as discharge adjustable guide vanes in each stage due to the configuration of these compressors. In this section, we will also cover the compressor protection systems. The basics of surge protection will be presented, and the following facts will be reviewed. The overall concept of a surge control system is to reduce the system resistance, and thus prevent low velocities in the impeller. The concept of the surge control system will be discussed, and the important fact of coordinating all components will be covered. All instrumentation, controllers and associated valves must be properly sized to enable the system to work efficiently. A typical process system and performance curve for a constant speed centrifugal compressor are shown here. As previously discussed, the performance curve shows the head produced by the centrifugal compressor. In order to operate at the rated point, as seen here, the head produced by the centrifugal compressor must be in equilibrium with the head required by the process system, as depicted here. This can be done by positioning a control valve in the section or the discharge of the process system. When the valve is in the section, the operation is called section throttling. When it is in the discharge, the operation is called discharge throttling. The controlled process variable can be either pressure or flow. In either case, energy is lost, since there will always be a pressure drop across the control valve. The following figure shows a process system with section throttling only. The operation of section throttling is frequently misunderstood because the section pressure gauge is often upstream of the section throttle valve. This does not allow the actual compressor section pressure to be observed. To operate at a lower flow than design flow, the section throttle valve will be slightly closed. This will reduce the pressure at the compressor section, which will increase the head required by the process system, since, if you recall, head is linked to the section pressure as follows. So as you can see here, as the section pressure decreases, the head of the process system will increase. In addition, there will be an increase in volume flow into the compressor. This will result in a lower value of head required and horsepower required than for discharge throttling an equal amount. Usually, section throttling requires 3 to 5% less horsepower than discharge throttling for the same reduction in flow rate. Keep in mind, the greater the head rise of the performance curve, the greater the savings due to section throttling over discharge throttling. Throttling the section or discharge valve of the compressor will always result in process system energy losses. It is more efficient, however, to change the compressor curve than to throttle to accommodate any operation changes. The available methods to change the compressor curve are speed change or adjustable guide vanes to change the inlet gas angle. In this video, we'll cover these two methods in details. Now, since accurate control of the operating point can be attained without the use of throttle valves, then this is the most efficient method of process control. The following figure shows the same process system as seen in the previous video, but this time with compressor speed control. In this control scheme, there are no pressure control valves. Here again, the process can be flow controlled or pressure controlled in suction or discharge process system. However, the output of the controllers is run to the driver speed control system. In this manner, the exact amount of energy charge required to meet the process requirements will be applied, thus optimizing the efficiency of the process. In this system, the compressor produced energy is varied to meet changing process energy requirements. Take a look at the following performance curve. Here, by varying the compressor speed, different head capacity curves are obtained. You can see here as examples the head capacity curve for 90% compressor speed, 95%, 100%, and 105%. And here you can see the low flow limit or surge line. Let's assume the process head requirement are given by the following blue curve. If our compressor in this system is operating at 90% speed, then the operating point of this process is given by the intersection of the head capacity curve for 90% speed and the system head requirement, as depicted here. To this operating point corresponds one and only one set of flow and head, as seen here. Imagine now that the process system requires more flow and more head to be delivered by the compressor. This additional flow and head can be achieved by simply operating the compressor at a higher speed, let's say at 100%. The new operating point will correspond now to the intersection of the blue curve with the head capacity curve of the compressor, but this time at 100% speed. As you can see now, this new operating point has a higher flow and a higher head. What I want you to understand and remember from this discussion is that this method of varying the compressor produced head and flow is way more efficient and more accurate than throttling using suction or discharge valves. So I strongly advise you, if you are working on a new compressor project or looking for a control system for your existing compressor, to go for this option. In fact, today this is becoming the industry standard, and many compressor applications are considering the use of variable frequency electric motors, commonly called VFD. It is true that the initial cost of a VFD can be 2 to 3 times the cost of a fixed speed motor with throttle valves, but the long-term power savings can easily be justified. Now, the change of flow rate, compressor head and horsepower as a function of speed are provided by the fan laws, as seen here. Recall, we have seen these relationships in a previous video. But I would like to remind you that it is important to understand that these relationships are only approximate for compressors and become less accurate with increasing number of stages and gas density. Remember, the exact values of produced head and required horsepower should always be taken from the compressor curve provided by the vendor. When designing control systems with variable speed drives, care should be taken to ensure the driver and transmission system have sufficient power capability for the maximum speed operating point, based on the process system head required curve. This is because a 5% increase in speed and compressor flow will require a 16% increase in driver horsepower. Now, referring back to our performance curve, we have seen that a change of shaft speed provided a mean to vary the compressor characteristic curve and thus meet the exact system demand without energy loss. Keep in mind that two means of achieving this objective are available to you: variable speed control, as previously discussed, and inlet guide vane control. The speed control method varies the amount of compressor input energy by changing the impeller tip speed and therefore the flow and head. Let's have a closer look. This figure shows the schematic of an upper half impeller with the side plate removed, the tip speed, which is a function of impeller diameter and compressor speed, and here the gas relative velocity to the blade. The gas exit velocity is the resultant of these two vectors as depicted here. Now, by increasing the speed of the compressor, the blade tip will increase an equal amount, while the gas relative velocity will remain unchanged. This will result in a new gas exit velocity. Let's now get rid of the blade tip and relative velocities and keep only the gas exit velocities for the discussion that follows. Let's now plot the x component of these two vectors. As you can see here, increasing the compressor speed resulted in increased blade tip, which resulted in higher tangential velocity. Now, since the head of the compressor is proportional to the tip speed, which in our case here has increased, times the tangential velocity, which has also increased, then it becomes clear that increasing the speed of the compressor will increase the produced head. Adjustable speed prime movers that are available and that are used extensively in process industries include steam turbines, gas turbines, DC and variable frequency motors, and variable speed drive devices. The variable frequency motors, referred to as VFD, are becoming more and more popular and will gain in popularity in the near future. However, where the alternative of variable speed is not available, adjustable guide vanes can be used. Adjustable guide vanes vary the compressor characteristic curve by changing the velocity of the gas through the impeller. This is achieved by changing the inlet angle of the gas and therefore altering the velocity relative to the blades. Now take a look at the following 3D animation. It shows the working principle of inlet guide vanes. To put it simply, inlet guide vanes adjust the gas inlet angle to the impeller. The higher value of the velocity relative to the blades, the less head will be produced by the compressor. This results from reduction in exit tangential velocity due to the higher velocity relative to the blades. To better illustrate this concept, let's refer back to our upper half impeller schematic. If the inlet guide vanes are manipulated in such a way that the velocity relative to the blade is increased, as depicted here, then the resultant gas exit velocity will have a lower tangential velocity. Now, since the head of the compressor is proportional to the tip speed times the tangential velocity, and that the tip speed isn't changed and the tangential velocity has decreased, then it becomes clear that the action of inlet guide vanes resulted in reduced head produced by the compressor. Adjustable inlet guide vanes are limited in their application and are effective only for one stage of compression, since they vary the inlet gas flow to the impeller. Axial compressors can accommodate multiple stage inlet guide vane configurations and are frequently used. In the 3D model view that you can see here, the rotating vanes which are mounted on the rotor drum are seen from one end. The stationary vanes are mounted by means of supporting arrangement from the casing. Various arrangements exist for supporting the stationary vanes. Now, a view showing only the rows of rotating vanes in the upper half is seen here. And here, the same view, but this time with the casing completely removed. The rows of rotating vanes are seen here at a different angle. In this view, the stationary vanes, which are supported from the casing, are seen from one end. And now you can see them without the casing. Here you can see the rows of stationary vanes in relation to the bottom casing of the compressor. In general, the stationary vane arrangements are guided by supporting rings for variable flow requirements. On rotating the supporting rings, the angle of inclination of the stationary vanes can be changed. This is used to change the performance parameters when required. The following illustration gives a clearer view of the stationary vanes changing their angle of inclination simply on rotating the supporting rings. For multi-stage centrifugal compressors, however, adjustable guide vanes are not usually employed, since their effectiveness is limited only to the first stage. One exception is in multi-stage integral gear centrifugal compressors. In this design, accessibility to the inlet of each stage for guide vanes is available, and so they can be employed. Recently, compressor vendors have also added the option of adjustable discharge diffuser vanes to this design, as depicted here. The combined effect of adjustable inlet guide vanes and adjustable diffuser vanes produces a compressor curve with maximum areas of optimum efficiency. Now, before to finish off this video, I would like you to know that adjustable guide vanes, due to mechanical complexity, must be maintained in order to minimize guide vane friction, which can result in lack of guide vane movement. I strongly advise you to consider purchase to the guide vane actuator and control arm assemblies. This is done to minimize the possibility of excessive assembly friction. Remember, the guide vane assembly is a system and must be treated as such. Finally, in the application of constant speed multi-stage centrifugal compressors, adjustable guide vanes cannot efficiently be used. Therefore, for these applications, suction throttling is usually used to vary the operating point of the compressor. Keep in mind that suction throttling is a system resistance change, while adjustable guide vanes do not introduce pressure drop into the suction of the compressor. They only alter the angle of the inlet gas to the impeller and thus vary the velocity of the gas relative to the blades. After examining the compressor control systems, let's now shift our attention to compressor protection systems. The function of any protection system is to prevent damage to the compressor unit by taking immediate action to remove the cause of potential damage. In general, compressor protection systems fall into three categories: overspeed, condition monitoring, and surge. All variable speed driven compressor units are protected against excessive overspeed. The industry accepted practice is to shut down the unit if the operating speed exceeds 110% of the compressor maximum speed. All compressor units are protected against operating conditions that can cause damage to any component in the unit, like seals or bearings, for instance. Upon reaching the condition value determined by the equipment vendor, the compressor will be immediately shut down. The usual condition protection systems are listed here. They include high shaft vibration, excessive axial displacement, low lube oil pressure, low control oil pressure, low seal oil differential pressure, high bearing pad temperature, and high process gas temperature. Most condition protection systems require a 2 out of 3 vote to permit shutdown of the compressor unit. This is to prevent shutdowns of the compressor resulting from instrument failure. In these systems, all condition protection devices must be supplied in triplicate. The one exception is usually shaft vibration, since the level of shaft vibration varies around the orbit of the shaft in the bearing. The third protection system commonly used for compressors is surge. Now, if any possibility exists that will cause the head required by the process system to exceed the head produced by the compressor, then surge protection must be employed. A surge protection system prevents surge by immediately reducing the head required by the process system. As discussed in a previous video, every compressor curve has the characteristic of increasing flow throughput for decreasing head required by the process system. The cause of surge, if you recall, is low flow throughput. Therefore, rapidly increasing the compressor flow throughput will prevent surge. And the fastest way to reduce the head required by any process system is to reduce the discharge pressure. Since, if you recall, the discharge pressure and the head are linked by the following formula. So as you can see here, if you reduce the discharge pressure, the head required by the process system will be reduced. The operation of reducing the discharge pressure of the compressor can be done rapidly by opening the bypass or surge control valve of the compressor. The following figure shows a typical schematic for a surge protection system. The surge controller that you can see here functions as follows. The input is the operating point, usually defined by flow and pressure differential, which is the discharge pressure minus the suction pressure of the compressor. The set point of the controller is the surge control line, and the output to immediately open the surge control valve is activated if the operating point is lower than the surge control line. Let's assume in our case here that our operating point is located here, so to the left of the surge control line. In this case, the controller will trigger an output signal to open the valve. This action will reduce the head required by the process system and will increase the compressor flow throughput, which will protect the compressor from surge. And the new operating point will move to the right of the surge control line as depicted here. Finally, note that an industry-accepted practice is to set the surge control line at surge flow plus a safety margin of 5 to 10%.